Oh my days. Oh my days. Right. So I think before we carry on and do any more programming, we need to minimize this problem, which means on all of our ray tracing shaders, we need to simply put a maximum for loop on it. Because it's doing so. I don't know which one was being caught though. Because you're just going over a number of spheres. Oh, it was going at is the tile binner. Maybe. Maybe it's the tile binning. Yeah, okay. We're just gonna not fly too close to the camera. That's how we'll solve it. I got an can I put like a min-max on it? Yeah, we'll put a min-max on it to stop that. But I think all of our ray tracing shaders, we should maybe put a max iteration. Anything with like a while loop, we'll do a max iteration on it. So that will stop us from doing any infinite loop problems, but it won't stop us from any garbage information doing these array indexing. So I think when we do any more of that, we should definitely put those safeguards in, and that should hopefully minimize the amount of crashes we get. But we'll get some graphical artifacts because shaders will just end early and maybe not put a pixel out. But yeah. Right, so back to that sort of spaceship looking code. It was already cool and everything, but we kind of want to just say, okay, well we just want to, we'll like we'll max it with, should we max it with like, so you just want to max the Z, I think. If you max the Z, it was very weird because we could go off the screen. We've been off the screen before, but it's just when you come too close. So if we max the Z, I think that might just stop us from encountering that problem again. So let's just say 10. Maybe it's not enough. Let's say 50. So we do sync just in case. Yeah, I think I'll hard kill my computer if it crashes again. I'm getting scared. That's too close still, isn't it? I want it to stop by the time it gets there. It's max 100. Oh, that's center position. That's why. We mean offset. Right. Wait, let me... Oh, that's already moved it back. Okay, it's too far. Let's try 20. Sync there. Right, that's 20. Let's try 10. See, it was already closer. Oh. Interesting. We should probably max... See, it would make the spheres all squish up if we move it too close, which would be quite weird. Maybe we can... I don't know. Nah, let's not bother with that. Let's do the offset. Although we should probably have a fixed Z then. Yeah, let's just say a plus 100. Wait, what, 150? Yeah, let's just say we're at 100. Because 100 was fine before. That was pretty close. So let's just say it maxes at 0. The offset from 100. And then we won't bother changing the Y because we've got the camera controls now. And that should... That's the closest it can get. And you go down as well. All right. Awesome. Now it's time to build some form of BVH. So remember earlier in the stream we was talking about the whole Morton Z curve thingy, right? So essentially we want to sort our spheres by that Morton Z curve. So I need to get some sort of like Morton Z curve 3D. I need to get this stuff, right? I need to get some utility stuff. So we want to go from a 3D coordinate to a 1D coordinate, basically. So, you know, that could be 0, 1, 2, 3. So by sorting our spheres by that sort of Morton code, we can sort of get them all next to each other in this sort of great way, because then we can sort of batch two of the spheres together like that, two like that, and then overall the four of them together in another box and build a BVH tree. And you know, as you can see, the Morton Z curve works at a micro level and every macro level as well, because there's another Z, another Z, another Z, and this is another Z as well, right? So it just every level it sort of goes out, so it's really sweet. We've just got to do this for 3D rather than 2D. If anyone has a link where there's some functions for this that we can just copy paste, that'd be really great. They were in here anyway. They were here, weren't they? They called it expand bits. That's why. Oh, right. Okay. So calculates a 30-bit Morton code from a given 3D location coordinate within a unit cube. Okay. Right, so it has like 1024. So what does it mean by 30-bit? Just using 30 bits? Expands a 10-bit integer to 30 bits, inserting 2 zeros. So I guess it's using 10 bits for each dimension. Someone's doing fireworks for some reason. They got cheap fireworks 10 days later after firework night. Right. Right, so all you're doing is just shifting it over, is that all you're doing? No, there's something more complicated than that. Because that's not 9, is it? It's 2, 4, 8. Yeah, that is 9, isn't it? And then interleaving the bits. Ah, that's pretty clever. Ah. Yeah. Okay, so let's just take this in video 1. It seems like it'll do the job. Yeah, for now this will do. We can always like build a proper library of stuff in a bit, but for now we just need this. So this will do that sort of Morton curve thing. So you're working with floats. So you're basically getting a step of 1020. 1024 is that? Yeah, because you're times it by 1024, so you're going from 0 to 1023 inclusively, right? So if we were to, so what we've got to remember is we've basically got a 1024 by 1024 by 1024 space that we work in. Like with this Morton 3D thing. So if we need more resolution, we need to go to a 60-bit version, right? And just tweak this. So, okay, that's interesting. So we can call it like Morton. Right. Let's just call it like Morton 30-bit. And we'll say XY. Wait a minute, what is it? So we're saying XYZ to, or 3D to 1D. Something like that. Boom. Okay, so that ought to be good enough. I don't know about the naming convention, to be honest. Maybe we should do 3D to 1D 30-bit. Yeah, and you can go the other way around. Or you could call it 3D to 30-bit. And then you can say 30-bit to 3D to do the other way around. But yeah, that should be enough for us. So effectively, we want to take all those spheres that we've put into the upload buffer. Bear in mind, they shouldn't really have gone into the upload buffer because we need to read write to that, because it's only write only memory, right? It's not really expressible in C, but it's write only memory. So really, we should put it in a temporary buffer somewhere. Like, so in the future, we'll be doing this all of this on the GPU, but it's just easier to do this on CPU because I haven't got a sorting function on the GPU yet. So we're just going to put in a temporary buffer. I need like, I need a temporary buffer somewhere of spheres. So we'll just call it G spheres. Good name. G spheres equal malloc. Don't use malloc. I never use malloc. Spheres. What's that max spheres number we've got? Spheres cap. Spheres cap. Good name. So let's allocate that. We'll chuck an assert down. Core assert. Spheres, please. Thank you. Right. Done. What's going on? Did the UK keyboard come and hit me in the face? What's going on here? News available. Wow. I don't know what keyboard key I pressed. I forgot. I know the Windows one. Right, let me nick that one into existence. I had a widget down there. It's gone. I don't want to do my widget. Because the speech marks are just in the most dumb place on the UK keyboard. They're basically where the 2 key is, and it swaps with the address. Oh, it's just so dumb. Okay, so anyway, so we've got this thing now. We'll dump them into there instead. Right. So we got our spheres. That's the destination place. We'll copy them all into there. What I would like to do then is use G spheres here. Then we do the mem copy. So we've got this thing called core copy element many. So we just say go into spheres, please, from G spheres, and we can just pass in a count, and it does all the size of stuff for us based on the element size of destination pointer or something like that. It's literally just memcopy, but with like, that basically times size of deref destination. So I've just got a bunch of these little utilities, which is proper nice, which is proper useful. Yeah, so let's get that, make sure. Okay, if the stream dies, I'll be back even quicker this time, I swear. Okay, I'll just make my machine. There we go. We're good. I want to change the controls, to be fair. Get the two hands on it. Fly the ship around. Bit fiddly. So it's like... Oh, man. It's J and K in it? Oh, J. Yeah, JK. That's what I want is the JK keys. What's wrong with the UK keyboard? I use UK. No. So what I don't like about the UK keyboard is to get the speed, like the double quotes and the quotes, right? Not on the same key. They're on a different key. And when you're a programmer, I think it's just better to have them on the same key. But yeah, and then the hash key is also difficult to get to, depending on... Actually, no. Yeah, the hash key... Yeah, maybe it's not a bad place, the hash key, to be fair. Depending on the keyboard you got. If you got like a Mac... If you go on a Mac, like... If you work on Mac, the way to access a hash key on a UK keyboard is ridiculous. You've got to do like 3 key presses to get it. But yeah, on a... Dude. Yeah, so... That's wrong. That's not a UK keyboard. They're telling lies. Oh no, this is it. So this is... Yeah, okay, this is right actually. On a Mac, they do the correction. They put the speech marks where the US one is. But on a standard UK keyboard, it's like that, right? The double quotes is above the 3. This is a Mac one as well. What is going on? Why is everything so different all the What? Yeah, this is the US keyboard layer where it's got the hash there instead of the pound. Yeah, the issue with the... Yeah, you got the... Yeah, anyway, it's all a bit weird. But yeah, I just prefer the US keyboard layout. The only problem is when I do pounds, I have to sort of get the symbol and paste it in. Basically. Maybe there's a key for it somewhere. Right, there we go. So what we're trying to do now. So now we can actually do some Morton curve sorting. Yeah, I still think it's present on the standard keyboards though. But the speed, it's just in the weird place. I like it on my right hand. Okay, so each sphere needs a Morton 1D, like 3D to 1D. And then... Right, so that needs -101. 3D to 1D. And then you want to... And also, we've got vectors. So 3D to 1D, and then we want to store that value per sphere, then sort all the spheres based on that. Right, so maybe we don't really do a mem copy. So we kind of want to have like another structure. Like we want to sort. Well, yeah, you probably want to have like a. Yeah, we'll do a U64 and we'll sort a U64. We'll cram an index into there or something. So you probably want all your spheres in a temporary thing. And we'll have the sphere sort keys, and they'll just point sort keys. Just do something like that. So all the sort keys, and we'll sort the sort keys, and then mem copy all over the place, I reckon. So you just go over all the 0 to spheres count, and you'll basically go over all the sort keys. Index equal G sphere sort keys index, and the first 30 bits, and you put the Morton code in the higher bits, and it'll sort it. And then you just do like a spheres index equal G spheres index, something like that. So now it's got to populate our sort keys array. So the sort keys is going to be basically cast into U64 Morton 3D. So you've got your normalized, your sign normalized point from -1 to 1. When you change that into normalized space, right? 0 to 1, like just unorm space. So we need to multiply it by 0.5 and then add 0.5. Okay, so that'll get us into into 0 to 1 space, and then you need to, so that will get you your high bits, so up by 32. We had to cast it to 64 because otherwise the shift left would have just not worked properly. So they're in the high bits now, meaning this, when you sort it, it will be the sort of the highest, the most important data, right? And then you cram in there the sphere index into your low. Right, then you cram the sphere index into the low bits, and then you just sort that whole sort key, and then hey, an intense lurker for me. Dollar on the hash on the 3 with the shift with Alt GR. Interesting. That'd probably be a good way to solve the problem when it's got to customize it. Yeah, it's by the enter in your keyboard. Yeah, it's not so bad. Yeah, the Mac has the problem with that. They've got to do Alt GR and Shift, and then 3 or something. It's like a complete crazy. You run an 8-bit do keyboard when it comes out. It looks so retro. 8-bit do. Have you got a link to that? Do you want a link in it so I can open up? Let's click on stream. I've got a keyboard behind me which I need to start using again, but I'm waiting for my hands to sort of heal back up. The Mac keyboard is really great because the key travel is really small, so I'm not sort of doing a lot of key press. But I need to, basically I lost the ball on using my hand exerciser and stretching my hands, so they got a bit weak again, but they're coming back. Just gotta, just work on the computer so much. I just gotta, keep rigid with it. But yeah, Awesome, thank you. Let's take a gander. Standing in there. Huh. Oh my days, that thing. It's got dials. Oh my days. Have you got these big red buttons as well? Just like I can imagine you're just like sitting there at your desk and you just like slam the desk and hit the button to sort of trigger an action. It's like, no, I pressed the wrong button. You know, I need to build my code. Slam the desk. That'd be cool. The only thing I'm not a fan of is these short keys. Like okay, on the enter key, this one. I like the UK enter key. It's just massive and you can sort of just put your fingers over here and you'll just hit it. I kind of not a big fan of this key because I typically will hit these. Maybe it's just because I'm not used to it, but still. I like the UK keyboard for that. I just don't like the layout. But yeah, that's cool. How much are these? Yeah, definitely looks quite retro. But yeah, they're kind of like a modern retro. You know, the sort of quality of modern day with like a retro sort of style. Oh. £5,000? What? No, how much is it? Amazon. I'm going to Amazon because I'll get doxed or whatever. But yeah, we'll see. £200. It's not that bad for a keyboard. Not that bad at all. Right. So now we've got our sort keys at the ready. We have to make a custom sort function. This is only the problem with C. Right. Sort it, mate. Void A, void B. And I think you can just do like return E64 deref B take A. I think it's that way around, sort high to low. Sorry, low to high. Yeah. Right. Sort it, mate. So what's interesting is we should color it by this order so we can actually debug visualize to make sure that that is sorted in the Z curve order. It's £90? Is it really only £90? When is this thing coming out? Is it out already? It was £90. I might as well just go and buy one now because it's like, it's the type of money where it's like, you know, £200, you kind of think about purchasing that, but £90 is like, you think about it less. Interesting. If they got on a special deal, it might be worth picking up. Crazy. I might take a look into that. Let's leave that open. Yeah, I've got a my wife bought me this keyboard. It's a good keyboard. Corsair. I think it's about £100. It's got the it's got cherry reds. It lights up like an, you know, RBG, you know. You know, it does the whole Gen Z RGB type of stuff, you know. All that lot. Right, Q sort, base putter, as C++ people call it. You sort in the G sphere sort keys, and you then sort in the number of members Is that right? Number of elements. Right. So number of elements is spheres count. And then size of U64. And then you pass in your sort it mate function pointer. Oh, we did it wrong. You know why? Because it needs to be const. Yeah. Right. So that'll sort all your things. So I think this is basically what we want, right? So, we could have a chance to blend up the computer again, but let's just double check it. So we go over here, put all our spheres in. It will sort of like up this, so this is going from like -1 to 1, and it's going over some step that we've defined at, we've got about 20 going across and 20 going down from -1 to 1. And if we land inside like a dumbbell looking shape, we will get, or like a weight, whatever you want to call it, right? I'm calling it dumbbell names. So if we're inside that shape, put a sphere down. Then so we up that, we add it to the sort key array, we do the Morton 3D coordinate to a 1D coordinate, which puts in the higher bits, so it will sort of define how the sorting thing is going to work, right? Because it makes the number much bigger than it does the low bits, right? It's in the higher bits. So we OR in the low bits the actual thing we want to be sorted. So it doesn't really, one change is that, and this is going to be bigger than all of those, basically. All the spheres we could possibly add. Then we add the sphere into there. For later, we sort all the sort keys from low to high. So they'll be sorted in Z-curve order. The more Z-curve order. Go over all the spheres. Pick out a key. Get the sphere index out the bottom bits. And then we go, okay. Sphere. Source index. All right, we need to bugger that one up. Right. So source index. Yeah, source index. Get it from gspheres, put it into the buffer, which gets uploaded to the GPU. Right, jobs are good. So if the stream crashes, I'll be right back super quick, I promise. Right, here we go. All right, we're good. So now apparently they're sorted, and yeah, I don't know what I was going to say there. But yeah. So now, how are we going to view the fact that they're sorted? Well, we're just going to color everything in, aren't we? So we'll be able to color it all in and just see exactly how it's sorted. So it's sorted from... so you've got a number of spheres. Where's our ray tracer? Right, so you're doing a ray trace. We could just color it by the sort. We could just be like, oh yeah, by the way, gsphere source index dot color. So you've got a 1D coordinate. How many spheres you've got? We could color it more red. You see, it's not .x, it's .color. So I think we can just like make it black. Or we could do red green, because that gets you 65,000, doesn't it? So you can basically do like a an OR equals like, shift lefted 16 of something that we're going to be filling in. So what we putting in there? So we want like a number that obviously needs to be clamped between 0 and 65,000. 65535, right? And the number that you're looking at putting in is whatever index. is, right? You're just putting in what index it is in the array. Yeah, so we'll go from red. Wait. We'll progressively get more green. Yeah, this is probably not a good idea. Because that'll just get more green, wouldn't it? Streamline expected crash. Hey. Yeah, well, if I say, if I assume that it's not going to crash, then it probably will crash, and then we'll be like, no. See, I don't know, like, what we're doing with this thing here, because you're just going to up it by the green first, and then it will finish one layer of green, and then add one onto the Z. Sorry, one onto the red. And then you'll go around all the greens again, and you'll see it'll be very weird. Yeah, I don't think this is the ideal way of doing it. Maybe we just do it along the. Let's just do it along on the Z, on the red. So 24, and then we'll just make sure that we need to divide it by something. So, you may divide it by spheres count or something. So we'll see it happen, but then the stuff on the far right or something will just be all red. We'll see it happen at the beginning though, about 255 of them, something like that. Needs to clamp just forward of the. Yeah, that's what we've done. We've clamped it, but we can still get a crash though, because if we get a buffer overflow on the GPU or an infinite loop, it will crash. And if we've told it there's spheres there and we've put some invalid data in, I forgot what happened. It happened before. It just doesn't like it. Right. So, what did we change? We've made that 0 now. So we put the alpha in there, right? Because it's red, green, blue, out. Wait. No. Right. That would have just made it invisible. Well, not really invisible because we ain't got that yet. Right, so put in the red channel. Jobs again. So, yeah, put in the red channel. That's all we've changed. We are now going to poke some extra stuff in there. So it shouldn't really crash, right? That divided by... Yeah, it won't crash on GPU. We can be assured on that one. Spheres count. So the problem is that it might crash CPU if that's 0, but it won't be. Rightio, let's go. Right, so we're not coloring it in correctly in the shader now. So let's go to the color. There's a count sphere color. This is our boy that we're looking for. So right now we just use the normal. So let's get the color and we're going to light it. No. Let's do another one. Let's do an elif and an else, right? So we're just going to want to display whatever the packed color is for this guy. Okay. Whoops, that's not going to compile anything. Oh, it is. Yeah, multiple reasons for crash, maybe. Right, so I'm seeing absolutely nothing. Nothing. Ugh. 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 So, yeah, summing up with the color being passed in. Alpha, blue, green, red. So we ordered the bits on. Comes in 0245. What is going on? Let's make them all red. See if the computer likes that. Right, there's our reds. So, why are you not red? What's up with my clamp? I did it the wrong way around, didn't it? No? Wait, yeah. Yeah, that's going to give me... Right, wrong way around. It's mod, isn't it? No, not mod. Well, we could mod it. Yeah, why don't we mod it? Yeah, because that will stop you from going over spheres count. Yeah, because that would have given you 0 to 1. And then gone over it eventually. Right. So the thing is we're moving the cam. Yeah, we're moving the ship and not the camera. I'm calling it a ship now. Look at me go. Right, I can't. Yeah, you know what? I don't like that. Because I want to see exactly where it starts. We should if we do the divide, and let's make it one of them afloat, and then we. Okay, I'll make both of them. Oh, no. Yeah, then you do U32. I only did a C++ thing. Right. What the living what is going on? I got next bracket. Cool. So after that, you then just scale it by 255. Okay. Huh. I'm a little confused. Oh, should we be pumping in the source index into here instead? No, it's regular index. Yeah. That's correct. I'm clearly a math scrub. Right. I don't know if it's that side or this side, because see, they both got dark ones. It shouldn't be that way. Oh, or is it? Maybe they're going from one to the other. See, I don't know what we can do to... If we flipped our Z, we'll be able to see this, because we're just in the lit side. So if we flipped our Z, would that help? Like, you're doing the sorting. See, flipping the Z isn't going to help. Like, flipping it in local space. What is that going to do? Because you're sorting it. Right, you're sorting it there. Oh, then if I did a negative Z, because that's in sine norm. Yeah, then that'll work. Okay, perfect. So we're seeing it the other way around. So I see this going along. Yeah, so it's doing it across the x-axis. Or is it? Because these are the darkest, right? And then like these are the next. It's going x then y. Okay, so I think our coloring is wrong, or that what we're coloring it in is wrong, or the Z curve data is wrong, whatever it is. We should be seeing it in this sort of like Z curve order, right? Where it's just yeah, it's just making these sort of Z. So that should be darkest, second darkest, and so on, right? We should be seeing it like that. So when we're punching in index, that's where it's putting. So we're sorting all the sort keys. Yeah, I think it's sorting it by... That's the right index, right? Because that's the destination. You're using the sorted index, so it should be in the right order. Right, let's use source index and just see how it looks. If this works, I'm going to be confused. Right, let me flip it the other way because it seems like it's on the other side now. Right, these definitely seem darkest. So, okay, so if we put it back to where we were, I think it's something wrong with what we're passing in. I think I know why. Our scale. Yeah, I know what the problem is. This Morton Z curve function times it by 1024. So, you know, you should really position stuff in this sort of space, in a stepping space of this 1024 or whatever. So we need to sort of remap it from. So it needs to be from minus 101. Yeah, I'm not sure what I want to. What I want to do. Yeah, so it's using 10 bits for each. So that wants it in like a normalized space, isn't it? And it's gonna move it up. I don't know if that's a good idea to make it automatic, right? But maybe the clamping is reasonable thing to do, but not the whole multiplier. So we've got it in minus 1 to 1, and then we do it. And our stepping is like 20. We got essentially from minus 1 to 1. We've got 20 different cells, whereas the Morton sort of curve thing has 1024 cells. So I think that's the reason why it's doing it along the x-axis first, because of that, really. So if we times this by, let's just have a bit of fun. Let's times this by 20. Is that right? That's not a good one, is it? Do we times it by... So if we've got it in minus 101, we've made it from 0 to 1 by doing this. And so essentially we've got it from... so essentially we've got 20 different cells. Right, so we need to essentially go from 20... What's the way we need to map? If we're going to 1024. So 51.2. So if you times our numbers by 51.2, we should be able to see better times. We should see that make more sense, right? No, still the same. Okay, so I got that completely wrong. Don't mind me. That's right. Okay, so that's not the problem then. So maybe we should debug print a few things out and just see sort of what see if it makes sense, right? So we want to print out core debug, get open core. What? Oh, core print basic, that's what I want. So I want to print out that. And we'll do like our own. So it turns it to a string and just prints it out nicely, basically, in the terminal. So it's their own little ones. So we're like, oh yeah, we've got 0. Yeah, so let's just do like, and then we do one across the X, one across the Y. So we could repeat that 4 times and do some 3D thing, but I think that's really it's got to be a. What did that? What took the address here for the float, isn't it? Damn it. Can I call this thing like? Because the problem with like using generic is that it doesn't. It has to have everything has to semantically check out. So type checking and all that has to work out. Yeah. So if you pass in an expression as an integer, the floating point code has to compile perfectly fine. And same with any of the other types. That's why it's a bit annoying. What? Does that compile? Maybe not. I thought it would be like it's not like a switch statement though. I think it's like an expression. So maybe you can't do comma operator because you're declaring something. Well, you can do this, right? You can do something like u64 underscore v, whatever. And then no, you. Oh yeah, you can. You can do that. Then you just got to do basically VV underscore, put in brackets, do a comma operator, and then do that basically. Super hacky. But that ought to be good enough and work. So it's made the name different enough, so it shouldn't hopefully clash. Where's the... Right, compiles. Finally. Right, so we should be able to see this. Alright, so in the terminal we run it. So we're seeing the whole string being printed. This is what I was trying to use it for, right? There you go. Oh, I could have done it with a function as well. That's a good point. Yeah, that's another good point actually. So those went really big. Oh yeah, 0, 1. Whoops. Yeah, but still. Yes, that makes sense, right? You're doing along the x. Yeah. Sorry, if I did 0.01, that would have been probably better. Been a lot lower of a number. Because it's 0 to 1, the way the function works. Right. So it goes along the y coordinate first, then the x coordinate, and then the z coordinate. I think. Let's read into that a bit more. No, x is definitely higher. Right, this is just a clamp. We can simplify this. Let's get the music back. Yeah, there we go. Yeah, so it's just in that times, you know, and you're doing expand bits. 10 bits to 30 bits. And then it's it. I guess how it should work, right? Is this a ray tracer? Yeah. So it's ray tracing spheres right now. We've technically tiled them on the screen, but we're trying to do some BVH building. We're trying to build these sort of boxes around these guys, but we're trying to sort out grouping them closer together with a thing known as a Morton Z curve. We're just trying to debug what's going on, really. So why is the y coordinate making a smaller number? Oh, but it does say that. Right. It does. This is where we've copied the code from. It is... Yeah, maybe the y is a... Maybe it isn't on the y-axis first. Okay. So maybe if we look at this now, do we see that? Y then x. It's very hard to see. And then it's z last. So that's why I explained the z gets... Right. So we're sorting on the Y first. So where's the darkest one? It's hard to tell, isn't it? So why don't we go up? Why don't we scale it by... If we scale it by 4 more times or something like that. We'll see it, you know, let's times it by 8 times. We'll see a lot more significant steps in color. So we should be able to identify what the first one is, right? Okay. So this looks better. So clearly it's going, that one's first, second, third, fourth, fifth, sixth. This is not Z curve order, is it? Like we're expecting it to be, so it is going off along the X first. But we expect it to be Z curving, right? We move this around. We expect to see it sort of going off into the distance or going down, you know, making a Z shape in 3D. We're not seeing that. So something is wrong. I've just got to figure out why. So just make sure our coloring is right. So we're doing our... Right. So why don't we get rid of the multiply and let's make the multiply explicit. Right, so you explicitly do it outside. So we then do a multiply by 1024 outside here. Okay. Great. So what does that get us now? So now it means we can test it out in here and see it actually behave better. So we can be like, okay, 1, 1, 1, 1, and we'll see an order like from, it would say like 0, 1, 2, 3, basically, right? So let's have a look at that. So 0, 4, 2, 6. So it seems like it's going along the Z first. So should we do another, should we... No, it's going along the Y first. I am so confused with what is going on right now. So Y is first. So let's get a Z coordinate in there as well. Yeah, let's get a Z coordinate in there as well. Okay. 0, 1, 2. So Z and Y. So Z is first. Y is second. And obviously X coordinate is the least priority. Okay. So if we take a look at the Morton thing, we see that so Z is first, Y is second. Okay. So I guess we can change that if we wanted to, but I guess it might, I don't know. Yeah, if we wanted to, if it made sense for us, I guess we can change the way that works, right? But anywho, let's just keep it because I don't think it ultimately matters, right? So based on that knowledge now, Z, Y, then X. And obviously 3 would be these two on, right? We can test that out. So you can do, like we'll literally invert this the other way around. That would be in Morton order. Look at me go. Right, so 0, 0, 0, the Z goes on, right, then it's the Y goes Y, then Z and Y, and then just X, right? And that'll, and so on, repeat it that way. And that's the Z curve order. But why aren't we seeing that reflected in the colors? So we're sorting them by the result of that. Am I doing something dodgy with this? I'm saying, hey, convert U to a 64-bit number, shift right by 32, or shift left by 32. So put in the high bits. Let's follow this around. U64, allocate, it's all fine. So we're punching in at the sphere index that we'll put in a number. See, I still have a bit of a feeling. So if we times it by 20. Oh wait, that's our step. We should already have a number which says like, what is the sort of resolution? So we've got 20 by 20 by 20. So I'm multiplying that by the resolution. So now they should be laid out better, I guess. I don't know. Let's have a go, see how that goes. That hasn't changed anything visually. Okay, so you're getting back you've taken your position in local space. And then you're turning it from a 3D coordinate into this sort of like 1D coordinate, which is sorted by sort of the Z curve. Order. It's a sort of intermorton order, basically. Shift left by 32 after being casted into this. And casting definitely takes priority. Let's all confused. Yeah, that's definitely gonna work, right? Then you sort all your spheres. Right, let's do A and B the other way around. I think it's just gonna go the other way around. Like, I don't think it's gonna be a problem. Right, what is that? Let's flip the Z back. Yeah, it's just upside down, it's just the other way. Okay, that's fine. So it's something from low to high. That's all we've done. So should we print out the... Yes, the next thing we can do to debug it is print out the index equal. So we'll fish out the Morton in order index, right? Morton order index 32. We'll cast it into U32 at the end. Right, see what we get there. Right, what are these numbers? We're seeing a repeat, isn't it? Are we seeing a repeat? 9.6. Well, I don't know what we should be seeing. No. Are they even sorted? Because what we expect to see, we fish this out. They're not even sorted. Sort keys, that's a pointer to the sort keys. Yeah, something's definitely wrong with the sort then. Yeah, so they're not even being sorted. It would make sense they're not even being sorted. I don't know why I didn't pick that out right away. Because if you think about it, we're going over the Z first, then the Y, and then the X. Okay, sorry. Yeah, we're going over Z, Y, then X. But technically it looks like the X is going first, right? That's because it's the most inner loop. So this would make sense. Okay. So now we know that the sort function is not working. Okay. So why isn't it working? Like, so we're using qsort. We're doing base number of members, elements, yeah. Size in each bytes, yeah. Using the compare function, yeah. So we're doing that one. That's the number of spheres we've put in, aka number of sort keys. That's the size of each element. Here's our guy. We're doing that, take that. Oh, I see, U64. Whoopsie. So what do we do? Because that's gonna wait a minute. So U64 take another U64. No, let's get you assigned a number. Right, but they're so big. Yeah, that's the problem. They're so big. So we need to shift it right. Shift it right by 32. Yeah, something like that. It's wrapping and it's a massive number. I don't think the wrapping's the problem. The wrapping's fine if it's assigned a number of the same size. So if it's a signed number of the same size, that's fine, but it's a signed number of a different size. So I think the way it's being converted is wrong. It's something like that. So I basically need to do something really horrible looking. Something like that, I think. Then you do that, take that, and then it will be the equivalent of that as signed. Yeah, I think it's fine. Yeah, it's fine because we want minus, because this wants to be returned. -1 means, or less than 0 means something. Like B goes after A or A goes after B, something like that. And then +1 means the opposite of that. And then 0 means basically the equal. So doing the takeaway thing is fine, but it's because they were both 64-bit numbers. And when you did a takeaway of those, and then it got, like, they were only in the high bits. So this was the problem. They were only in the high bits, like the 32 high bits, and the low bits were all so it might have been sorting by the sphere index because the top bits would have got truncated when it casted it down, or something like that. It was something like that, at least, that was going on. That should fix it. Yes, we're in business. Are we? I don't know. So it is Z first, isn't it? So and then it's by Y, and then it's by X. Like that's just the way it is. So if we follow sort it, mate. Let's get rid of this now. We learned how the function worked. And then all we need to do is remove that multiplied by 8 to make it more. Do I want to flip the Z as well the other way, I think? Excellent. Excellent. Mr. Burns, man. I watched Simpsons for ages. Yeah, I think that's looking like Z curve order. We've really got to see. I don't really have a rotate, so it might be a bit hard to see. We could always change the X, Y, Z the other way around, but let's actually probably just multiply it by 8 again. Right. I don't know. It's really hard to tell. I don't know what's an easy way. So you could probably do every 4. Okay, so look at the Z curve. You could say every 4 get a red value. So 0 red, 1 like 1/4 red, 2/4 red, all red. And then you could probably do a macro level of that. So every 16 get green, and then every get blue. And you basically see, yeah, I think that might be a better way to do it. So you could probably do something like so do you want to say like mod 4? Yes, I think you say mod 4 gets you the red. So mod 4 won't bother with the clamping. Mod 4 gets you the red. So mod 4 times, is it times? Mod 4 times 64 in it. The problem is like maybe times 63. It's not correct, but it's good enough. It's the easiest to think. So I'll get you all red, basically all red it. It should be mod 4. What am I doing? Not divided by. Cool. And then we want mod 16, and that will get you green. Wait. Yeah, that will be green. RG. So it's 8. And then blue will be the sort of bigger one than that. So that'll get your Z to your outer Z. And then I guess we could just do that for now. We'll see how it looks, and then we can introduce the blue if it makes sense. Huh. I'm not sure what, because it was starting here. So why are we seeing a bunch of zeros? Yeah. Yeah, it does make sense, doesn't it? Yeah, that's whether they should become blue or something. So we should probably need the blue on it as well. Maybe. Not sure if there's a good way to visualize this. So you need 4. Is it 16 times 4? So I think it's 64. And then rather than being times, so what's 64? Yes, it's 16. So do 15. Because that will get you just under 256. Then 64 times 3. Yeah. Let's try that. Right, is this a good way of visualizing it or not? I can't see it being a good way to visualize it as some form of order. But also this thing here, yeah, it's sort of high to low. It's high to low order, I think. Whoops. Right. I think partly what's making it hard to visualize as well is yeah, okay, maybe it's not a good idea to color it. That's fine. Right, let's just put it back to red and we'll get rid of the color. Let's just use the printing at least. So we want to change the sort function and then we can start doing the BVH thing. So if we did A take B, okay, so A take B is low to high and then it's the other way around for high to low. Yeah, so here's the order. Right, so let's start building this BVH then on the GPU. So we've got it in some form of like order. So we could take these two, put them together. These two, put them together ideally. Is that right though? Alright, so then let's revisit that sort of block thing and we'll re-talk about that again. Let's get the colors back. Those lovely normal colors. There we go. So I want to try and put a BVH around here. Basically, and they're sorted now. So it means that effectively the spheres are next to each other. The spheres that are next to each other in a linear array are next to each other as a 3D coordinate, basically. There might be a bit of a distance apart on some edge cases, but for the most part, they're going to be next to each other. So let's do, so effectively, like, I want to do a simplified version of what this article is doing. I'll drop this in the chat. Right. So it also links to a paper as well, which further describes it. But effectively, this one has a way of, has an extra step, I feel. So this one defines how you can basically do highly parallel sorting on the GPU. They have to be sorted in Morton Z curve order. This is what we've been trying to do for the past hour. Let's get Milton out. So what we've done now, it will load up. There we go. So what we've done now is you can have your spheres in 3D space. And this one would have 0, this would be 1, this would be 2, and this would be 3. So we can ideally wrap one bounding box around these two, another bounding box around these two, and then a bounding box around these guys, right? So that will create a tree like this, where this box is that node, and this box is this node, and this box is this node here. Right? And you're basically creating this massive binary tree, and this is the bounding volume hierarchy. So the key to it, that setup, that sort of Morton code thing was not really, like, this was, I think, defined by this linear BVH paper from years ago, I think. So this sort of paper, so there's a paper made by the person who made this blog, and he does link to it in this page. But the key takeaway they make is basically doing this algorithm in a very highly parallel way. They do this extra step though, where they sort of like process, or they figure out which two nodes link to each other, and I think makes it more optimized or something. I'm not quite sure. So they make it so it's slightly more optimized in some cases, I imagine. But what I want to try and do is a very simplified version of this, because this involves doing there's this find split function that they do, and it's basically like a binary search and whatever. And we could do this, but I kind of want to see like how much this actually helps, and also what sort of speed penalty do you pay. So I just want to do the simplest way first, and then we'll do this one afterwards. So the way that I've thought about doing it, and maybe this doesn't work, but let's just give it a go. So the idea is you've got this binary tree that you want to build, and the key takeaway that this paper makes, that they link to and they reference in this blog, is if you have, say you have 4 spheres in 3D space, and this is as a tree though, right? The idea is you have number of nodes. The number of leaf nodes can tell us the number of non-leaf nodes that you need in a binary tree. So that is basically n take 1, and that gets, all you need is 3, right, to link up a binary tree, right? So it's n number of leaf nodes minus 1, that's the number of leaf nodes you need. So basically, knowing this information, you can basically do it. So if your leaf nodes are sorted by location in space, so now we've sorted them in Morton Z-curve space, right? This Z-curve space, which means they'll be like next to each other in, like, we've taken them from this 2D sort of Morton curve space into a 1D space and then sorted it. So all the spheres which are next to each other in 3D are next to each other in this 1D array. So we can effectively just, like, we can just have our nodes in a buffer, and we can know exactly what they need to point to, just based on, like, if we know this is, like, so this is where it's like my sort of simple version, right? We know this number is like a power of, like, every time you just go past the power of 2, you need to make another layer, right? And you need to make another layer. So what we should be able to do is literally just figure out, and so this part is based off of the paper, like the parents, like you should just be able to know your parent based off like the power of 2, basically. Like, I think, this could be 1, this could be 2 and 3, right? And then these would be like 4, 5, 6, 7. So, this one would be, well, okay, sorry, it's an index, not a number. So this would be node 0, this would be node 1, node 2, 3, 4, 5, 6. So, this number you just use like the least, you basically work out like what power of 2 does it belong to. And so this one belongs to, is that right? So 1, so I think in my graph, yeah, let's make this a little bit deeper. Let's make this one a little bit deeper. Whoops, I need to make that a bit wider in it. So I'm gonna go 1, 2. This is so bad. Not even at all. Right. I don't know what I'm going to get from this, to be honest. Right. I wish I drew that better, but I didn't. Ought to be good enough, I reckon. So let's just draw the links. And then all will be clear. So I reckon what we can do to do this, so it's highly parallel. So these are our leaf nodes. These are our spheres in some 3D space. So we've got 8 of them, right? So, 8, take 1 is the number of leaf nodes we have, which is 7. Sorry, the number of non-leaf nodes that we have is 7. So all we should have to do, so this could be 0. So something to note about my BVH design is that it's a binary tree, right? So the couples sit next to each other in memory. So these two sit next to each other in memory. These two sit next to each other in memory. These two sit next to each other in memory. Okay? So by doing that, this node is implicit and doesn't exist. This is actually 0. This is actually 1. This is 2. This will be 3. This will be 4. This will be 5. Right? So based on this information, what can we do to, like, effectively all we need to do is say each thread gets a node, and it can patch, it can tell us what its children are, basically. So if you get 0 for your thread in a compute unit, how do you link to 2 and 3 just with pure maths? So you can be like, what is my nearest power of 2 or something? And I guess it'd be 0. Sorry. There's no power to, it's 1, isn't it? 1 is, yeah. So it's 1. So 1 is 2 to the power of 0, isn't it? Yes, you do 1. Yeah, so maybe it needs to be 1 based. So it's 1, 2, 3, 4, 5, and then we take away 1 afterwards. So yeah, maybe we do given my index plus 1, where's my nearest power of 2? See, I'm not sure if this will work. And then it'll say, well, it's 1. So it'd be power of 2, it'd be 0. Yes, this is a really bad number to work with. Let's go with this one. Because that goes 2, 3, 4, 5. Um, Because that'll go all the way up to 8. There's 0, 1, 2, 3, 4, 5, 6. Yeah, something's a little bit off here. Yeah, maybe if I number it back the other way. Let's say 0, 1, 2, 3, 4, 5, 6. That'd be 7, 8, 9, 10, 11, 12, 13, 14. Yeah, this doesn't quite work. It's always 2. So root is 2. Yeah, I don't know if we're off by 2. I'm not sure. So what you're saying is do 2 here. 3, 4, 5, 6, 7, 8. Yeah, that makes sense, doesn't it? Yeah, base is 2. Not in this situation. I'm not sure what you mean by that. So you're saying do 2, 3, 4, 5. Oh. Oh yeah, because you're saying in my situation where, okay, I do the grouping. Right. 2, 3, 4, 5, 6, 7. And then 8. So yeah, you'd do... Right, so 2 to the power, yeah. So you can basically work out with the, with the count leading zeros or whatever it is, you can work out which one of these you are. So you'll be like, okay, let's go, I'm node 5. No, sorry, I'm node 2. How do I work out my 2 children nodes to sort of match up in this tree? Because then in theory you can just spawn a thread, a bunch of threads which can just get a node, and they can tell you exactly what their children are and just set them, and then no other threads is hitting the same piece of memory, right? Thank you, sir. I really appreciate it. So how do we get 4 and 5 from 2? And then let's try and do the 3 one. Or maybe 3 makes more sense to do first, and then we'll translate back. Depth to the power of 2 power of depth. Index is the leftmost node. Though it's really memory inefficient way of encoding a binary tree. What do you mean memory inefficient way? Do you mean that if it's not fully occupied? Yes, I think with this method it's going to be balanced. It's going to be a balanced tree always, where possible. Obviously, if you don't have a power of 2 leaf nodes, it's not going to be fully balanced. Or this one wouldn't exist, for instance, right? But these ones will. Yeah. So what you're saying is 2 to the power of depth gets you the leftmost node. Is it this one? So where's 2? Oh, this is interesting. Oh, this is like a binary heap, so you can get an implicit. That's another way of doing it. We could get an implicit. Like, you don't even need to assign numbers. That's why we keep having this problem. That's why we keep having this problem. Like, every time I'm like, oh, we have to calculate the number and store it somewhere. But then I realize that it's just But then, like, someone links me to something where it's probably calculatable. So you don't really need to store it, and you can just calculate, because that's what happened with the Z curve thing or something like that. We were trying to fit it into a grid, but then all that was but then there was a better way to do it, which was with the Z curve thing, and you could translate a 3D coordinate into a 1D coordinate, and it was already sorted that way. So maybe we can have like an implicitly defined tree with just a bit of maths, basically. So you're saying that to get the parent node is I take 1 divided by 2. So 3, take 1, divided by 2, gives you 1. So traversing it, so you get the left child is I times 2 plus 1. This is genius. So we could just do, wait a minute. So if we have an array of elements. Yes, this is one method we could definitely do. But I think when we end up doing this whole sort of paper here, it might not be compatible with this, that's for sure. Yeah, it won't be compatible because it does a little bit of some intelligent thing. But we should see how well this can get us, because then we won't need to actually make a tree. We could just have we can just store the axis line bounding box, and the tree is implicit. That'd be pretty incredible. So you're literally just doing. So okay, so I guess we need a root node then. We need a root node, and that'll just fill up the whole thing. Maybe you can skip the root node. We'll leave it in as 0 or something. And we only want to really traverse down anyway. Wait a minute. Root element be at 0. So if I did 3, take 1 divided by 2. 1. Yeah, alright. Shows the indices of the other nodes for the ith. Right, so okay, so they've just got values. These are values. Ignore these. Right, 0, 0, 1, 2, 3, 4, 5. Yeah, this is exactly what we want. Yeah, because you already know the depth of the BVH. Precandle array. Yeah, this would be amazing. So if we've already sorted our things in Z curve order, so we still have to build the BVH. So we've still got to build the BVH. So we've still got to do a multi-threaded build of the AABB at least. So we can do some like atomic min-max, basically. Something like this. Well, I don't know how you'd do that actually. We'll think about that. That's the next problem to solve. So we should. Right, so what are we trying to do now then? So what is this array? Yeah, so these are BVH. These are our BVH nodes. Yes, these are our BVH nodes, and we need to. So we just need to essentially clear all of this memory to something sensible. build the axis line bounding boxes, and then like from the leaf nodes, basically. And then what happens, so if you're a leaf node, we need to point to probably 2 spheres. But you can do that implicitly. So you'll be like, right, on 5. Okay, so what's this one? So on level 3, so on these leaf nodes, I guess, you'll point to 2 more spheres. So it needs to be remapped into something else. So this is 0, 1, 2, 3, 4, 5. So the last 6. Yes, you need to do the thing where that sort of power of 2 thing. Yeah, so imagine this is the last row, right? You need to do the least significant bit on it. You realize it's 4. So you sort of round it down to the nearest power of 2. You realize it's 4. Then you sort of subtract that from the number. And that'll get you basically the array that you need to index the spheres in. Yeah, so that can be implicit too. That's pretty cool. So we can implicitly index that array as well. Right. So now we just have to figure out a way how to do the axis line bounding box. So they did this in the paper. I don't know how they did it. The basic idea is to only recalculate the bounding boxes according to the nodes. According to the new locations, keeping the hierarchy the same. Right, bounding box calculation. This is the bit we're kind of missing. How to do this in a multi-threaded way. Now we have a hierarchy of nodes in place. The only thing left to do is assign a conservative bounding box for each of them. The approach I adopted in my paper is to do parallel bottom-up reduction, where each thread starts on a single leaf, walks towards the root to find, so you start one thread on each leaf, and they all walk up. To find the bounding volume of a given node, the thread simply looks up the bounding boxes of its children, calculates their union. To avoid duplicate work, the idea is to use an atomic flag per node to terminate the first thread. To terminate the first thread that enters it, while letting the second thread one go through. This ensures that every node gets processed only once. That's pretty genius. And this was done in 2013, people. Back when I was doing JavaScript, what? The bounding box calculation. Yeah, so I think we already get the idea. That's pretty genius. So I think we can actually just go full ham now. So basically, you want to do like a. Do they use? So they use an atomic flag. But if we just clear the memory of the bounding boxes to positive infinity minus infinity for the min-max, right? Then we just atomic min-max them. So you're saying atomic flag. Yeah, you atomic min-max, and then you will have another flag that we need to set somehow. So I think when we do the atomic min-max, doesn't it give you an old value back? And if it gives you an old value back and it is infinity, then we terminate the thread, right? Because you're the first one to set it. So I think that's the way those things work. Let's just quickly check HLSL min. Because, you know, all works the same. Do they return an old value? No, sorry, they return the new min value, isn't it? So they can return the original value back out. Right, let's just quickly double check the spear Vs, because that's what we're using, obviously. Spear V is like op subgroup min. Screw this thing. Group min. fmin. Gotcha. Right, so result. It doesn't tell you what it returns, but you can just check GLSL. GLSL atomic min. And then OpenGL is probably like really bad docs as well. Returns the original contents of mem. That's exactly what we want. Oh, yes. Right, let's go. Let's make our shaders, guys. Let's go, let's go, let's go. So, we're on a new shader, and we're calling this one. This is getting so untidy, but that's fine. So this will be known as BVH, BVH clear, and you just want to clear your BVH. So you just want all your BVH nodes. Like, how many do we want to clear? Nodes count. Just going to clear all those guys to positive infinity, negative infinity, all that chance, right? Cool. Right. So the idea is you're just going to do some sort of like check. Just get in there. Something like that. And it's a 1D thing anyway, isn't it? Right, I can just type that out. It's pretty simple. Okay, so we're saying if SV, so you do like 32 in lockstep. If SV dispatch index.x is greater than or equal to BC BVH nodes count, then we obviously return. Now all we need to do is say BC, so that would be your node index. So I guess we could say node index, and then you just say BVH nodes node index equal, then we say dot. Now we need to look at our BVH, right? Because we did a thing. We made this BVH node for our BVH viewer. So now the BVH viewer just needs to be an access line bounding box. So we're defining, so we should just define its half dims. Right, so we kind of just need a min-max now. Min-max of the node, and we can, I think that'll be better. Yeah, so I think actually we need a center position for the viewer, but I think in general when we're doing sort of bounding box collision checks, I think you need them as min-max anyway. So it's probably better to have them as min-max. So here we're just gonna say dot min equals positive infinity. And then the max is going to be negative infinity. So this means when we min and max against it, when we min max against this thing, it will overwrite the infinity value for any value, basically. So if we min anything against that, it will overwrite the infinity always. So that's the clear, basically done. We just got to fire it off. Now we want to do this sort of calculate bounds. So how the calculate bounds is going to work. So we'll do 32 at a time in lockstep again. Calc bounds. Okay, so we calculate some bounds. It says it wants to start down at the leaf nodes. Right, so by knowing how many nodes you have in a tree, right, we want to, so we want to do that sort of number of leaf nodes thing, right? Or leaf nodes count, right? So leaf nodes count would be bit most significant? What's the bit index of the most significant bit? And you do that from this. I think it's like, is that right? So that'll get you like, what's the most significant bit set? Bear in mind you should never have 0. So if we get 4, yeah, so you know 0, 1, 2. So if you get 2, you do 1 shift left 2, and that'll get you 4. And then you do whatever your index is. Actually, no. Yeah, wherever your index is plus that, and that will get you one of these leaf nodes, ignoring these guys, as assuming these are your only leaf nodes, right? That's what we mean by leaf nodes. So that's your sort of base leaf node index. And to get like a number of leaf nodes, yeah, no, we'll just add it. So you're sort of saying node index is equal to sort of that plus your base node. And then, so you start off with the leaf nodes, and then you're going to say, if it's greater than the nodes, then return. Right, so, you know, you can't spawn less than 32 threads in a wave, for instance. So unfortunately, you're going to have, you know, each thread is going to get a node and then start going up the tree. Obviously, this tree is going to be probably quite big. Yeah. So obviously the rest would just be wasted. But it should be fine. But the tree is going to be massive, right? So the problem is you're going to walk 2 up the tree. There might be a better way to organize this where each wave gets... Because these 2 threads in a wave will go up, right? Do the atomic min. But they'll be doing the atomic min in the same wave. So really you can just do a wave. No, you can't, because it's 2 threads on the same wave. You can't really... I guess you can read your buddies one, but then the one after that is the other guy, and it could eventually be from a different wave anyway. So the problem is with this is you have 32 that are next to each other. The whole wave is going to be active for 32 of these going up, right? That's probably fine though, because that's just 2 to the power, 2 to the power of 32, isn't it? Which is 4 billion. So maybe that should be fine. Yeah, you're probably only using one wave anyway. Right. You're literally only going to be launching one wave to calculate the bounds. Yeah. Okay, so we'll do the simple thing and just use atomics, but it should be like pretty quick. I reckon. I don't think there's any dodgy, any sort of smart thing you do where you get massive speeds. So do like an atomic. So you want atomic max against the min. Is that right? No, sorry. Yeah, minimum against the min. We put the max value in there. So there's your source location. Oh, by the way, we didn't change the read writes. These are read writes. These, that's a write only. If you calculate max depth, you can find something. is a leaf node by checking its child exceeds the count. If you calculate max depth, you can find if something is a leaf node by checking. Yeah, you don't even have to do that. But yeah, I think that's, yeah, because, oh. Yeah, we should really have an unbalanced tree here. Yeah, we should draw something up. That's, one. Yeah, I don't think you need to even do that. I think there's a simple way to do it. So let's do, that. So you'll do, this would be 1. Is that right? Yeah, 1, 2, 3, 4, 5. In this case, 3, 4, and 5 are leaf nodes. So yeah, I guess we might have to do something like that, I'm not sure. So you do like, so basically you could have up to 4 here, but the last 3 are actually leaf nodes. Yeah, maybe you need something a bit more complicated to check this against. Yeah, you could just do, hey, if your leaf nodes, yeah, maybe that is the way you do it. Like Crimson Mania, you just check if your leftmost exceeds the bounds, then you are a leaf node. Yeah, that's probably the easiest way to check it because it's literally just like a simple check. Where did the thing go? It's literally like times 2 of index plus 1, and then a comparison check. I think that's probably the cheapest way to do it. Yeah, it seems pretty simple, I think. So is this right then? So your base leaf node index is 3. We're doing like, so the number of nodes we have is 5. The nearest power of 2 is 4. It would have gone from 4. That's not right then, given this. So what could we do to get that correct? We need to, like, we've launched. How do we get the number of leaf nodes for a given number? Maybe the best way is to send a HTTP request to ChatGPT, give it the numbers, wait for a request back, and then we've got our number. Oh, wait, then parse the JSON, and then we've got our number. That'll be it. No, so basically the idea is like, we've got, it is a balanced, well, it's not balanced. It's not really a balanced tree per se. Is this the way it would be done? Yeah, that's the way you'd do it. Model software, right? So yeah, a balanced tree would be, but you wouldn't have one. You'd have one hanging off each of them. Yeah. But why would you have this tree? Would this tree even be possible? I think it wouldn't be this way, would it? It's not that I want to know if it's a leaf node. I want to know. So the calculate bounds starts from the leaf nodes and then traverses up. So I need to just know how many leaf nodes there are. So I think I got an idea where actually this is not the correct tree. The correct tree would be one hanging off of here, and that one wouldn't exist, right? So, and why would that be the case? And that would be 5. But then why would you have one hanging off of each of them, right? So technically, that would then reduce back, would actually be 2 and 3 only. Is that right? So you've got like 3, basically I've got 3 spheres in the world. It would not make a tree like this. Will it? Actually, that's a better way of saying it. We've got 3 spheres in the world. What tree would it make? Yeah, it would make that tree. Would it make that tree? No, it wouldn't make that tree. It would make that tree. Well, no, it would make this tree. That's an extra layer. Huh. Let's have a think about it. Calculating the max depth should be easy. Because you can check the depth boundaries. You know a value of depth would be 3 nodes. Value 2 depth would be 7 nodes. Yeah, so you have the whole thing where it's like, hey, I got 3 leaf nodes. So the number of parents I need is n take 1, which gives me 2, right? Okay. So everything is power of 2 take 1. So yeah, so knowing the number of yes, I need to know the base offset for leaf nodes. So okay, so if the number of leaf nodes, so I got the total number which is 5, right? So then it's just so yeah, everything is power of 2 take 1. So I need to find is the amount of leaf nodes plus 1 divided by 2. Is it divided by 2? It's power, isn't it? So it might be n take 1 log 2, right? Something like that. N take 1 log 2, so 5 take 1, 4, get the nearest power to it's not right. Or log 2 take 1. So log 2 of that will be 4, take 1. Sorry, not 4. Right, the log 2 of that would be 0, 1, 2. Take 1, 1 shift left of that will get me 2, right? But for a balanced tree, the total number of nodes is 5. The max depth is 2. Yeah, I know that. Wait, so you check 2 times max depth plus 1. Yeah, I'm not trying to figure out if the node is out of bounds. I'm trying to figure out the number of leaf nodes from the total number of nodes. That's what I'm trying to work out. So I think it's that, right? So this is a cheap version of log 2, right? It's just getting the nearest power of 2 rounded down. Then we take away 1. Bear in mind, there's probably got to be a max in there somewhere. Then 1 shift left. I think that's right. So if we had... Wait, is it based on nodes count? So our nodes count is 5. It's balanced, right? Yeah, it's balanced. Yeah, it's going to be balanced. So I think it's 5, right? And then say if you did 7. Right, 6, 7. So you got 7. If I did nearest, that would have been 4. And it would rounded down. That's not right, is it? Oh, thank you, Dark Walker. Appreciate it, sir. Welcome. Appreciate the support. So in this case, it would be 4, right? But if you get rid of that node there, that's 6, it will still be 4. But we've got rid of that, and now it's actually... So you got 3 leaf nodes. It's probably something dead simple I'm not thinking about, right? So that's total of 5 nodes, but total of 6 nodes. Actually, would that even exist? Would this even exist? No, this wouldn't even exist. It's not possible, right? Because that's still 3 leaf nodes. Right, there's still 3 spheres in space, right? So you add another one, and then it creates these 2. Right, so that'd be 6, 7. So that makes sense then. So you take, that's 8 nodes. Is that right? 8 nodes. No, 7 nodes, isn't it? So maybe say 7 plus 1 log 2. That will get you 0, 1, 2, 3. Take away 1, get you 2. 1 shift left 2, gets you 4. And that's your base. So it might be this plus 1, get your log 2. Shift left that. After taking away 1. And then that will get you the base leaf node index. So let's say 5. You're saying 5 is the number of nodes I've got, plus 1, which is 6. Nearest log 2 is this one, which is 0, 1, 2. Take away 1, 1. 1 shift left 1 is 2. Right? And there's your... Wait. That's your base. It's not quite right, is it? It's not that. 5 take 2 is 3 though. And that would be... Wait, sorry, 0, 1, 2. Okay, let me run that again on the higher one. So you got 7. 7 plus 1 is 8. Log 2, that would be 3. Take away 1, 3. 1 shift left 3, 4. That's not right, is it? Yeah, it's still a little bit off. Is it divided by 2? It might be. Someone else did say that. It might be that then. So you do 5 plus 1. So 6 divided by 2. Be 3 in it. Right. Let's try that. Apologies for the person who said that originally. Super apologies if this is right. It seems right, doesn't it? 7 plus... Yeah. Yeah, that seems right, actually. That's even better. Because it's actually all pretty simple maths, isn't it? There's that plus 1. And it's just like a shift, basically. Obviously, we're not going to do that. We'll do divide by 2 because it makes more sense. So it'd be a base leaf node index. Pretty good. Yes, that'll work. So we've got our leaf nodes. Right. Thank you, guys. Thank you, Crimson Mania, and who else was it? The introducer. Appreciate it, guys. Sorry, I didn't try that out originally. Right, so we got each thread has a leaf node, and we're just going to walk up the tree. So if we walk up, so you got your node index, and so we should already have a few convenience functions, right? And this should just be called. So let's go into shared or whatever. I have like a BVH, BVH left child left, and you take in some like node index, right? So we'll have these all just encoded in here, child right and then parent. Sort of ways of like just traversing the tree. So we'll just grab all these, right? So parent is I divided by, is I take 1 divided by 2. Obviously, if you take 1, if you're 0, not really gonna work. So you should really obviously guard against that. So it's I times 2 plus 1. Right, makes sense now. Okay. Sweet. So we've got these nice handy dandy convenience functions. So we're just going to be going up the parent. So you're going to get your current bounds of your leaf node. So what's the bounds of our leaf node? So we need to take the 2. So we need to get the base. So we've got our base. But we also have our... so you want to know where your spheres, your 2 spheres are. Right, spheres base, or base spheres index. And your base spheres index is going to be dispatch index times by 2. Right, because it's leaf node index. Well, sorry, leaf, like, okay, 0, 1, 2, 3. That's what I mean by leaf node index. Times by 2 because there's 2 per leaf node. So you're going to point to 2 of them. So we get the 2 of the spheres, and we'll be like, so we need the spheres array. Calc. Yeah, so we just get the spheres array that we upload from the CPU. And then we just want to get the number of spheres. So, because we want to go out of bounds, right? So the left node will always be there, but the right node might not. Yes, the left node can be there. Yeah, but the right might always not be there. So in terms of this, so we can basically calculate the min-max bounds, and the first one we can set, and then we walk up the tree. So we just need to store it in the first one. So you first of all calculate your min-max. So your min is going to be equal to BC spheres, base sphere index, plus 0, I guess. Because we're going to be doing a plus 1 in a minute. Get your center position of your sphere, and your min. Oh, I guess there's a sphere radius as well. So you know what, we'll pull the whole sphere in, even though there's a color in there. Right, so call it S. S equal this. So you're saying S sub f32 times 3 s dot radius, right? So that's your min, and your max is add like that, right? So that's your bounding box around your sphere. And then what you need to do is say, okay, well, if my base sphere index plus 1 is less than the BC sphere nodes, yeah, but you're never, okay, if you have a left 1, like you're not just going to have one on the left, because that'll just go to there. So you only really have, yes, you always have a left and right, always. So you never need an if statement. Excellent. So you just repeat that again, do a plus 1, do the same thing, this time with a min f32 times 3 and min, this time a max with a max. Okay, I think that's pretty sensible. So you've now just computed the bounds of your leaf node, and now you simply set your current node and then you walk up the tree. So you do your while loop, and you're basically saying while my node index is set, it's kind of a do while, isn't it? Oh, you know, it's kind of cool we're doing a do while, even though I kind of hate them, because it means it can test my compiler out some more. Wait, is that right? Maybe not. Maybe not. Right, let's do the set. Oh, no, it is this way. Yeah, I'm not really a fan of do whiles. I always try and do them, and then it's never the case for do while. I have to rewrite it anyway. So I just find the if statement much better inside of an infinite while loop. So we just simply set them in the leaf node. Right, set them in the leaf node, but these, and then you want to go in here and say node index equal gfx BVH parent. Yeah, that's any go-tos, man. Then there's no need for any scope blocks, and there's less indentation. Way better. You got the parent, and then you want to do your atomic. Yeah, I think this do while is not right, as always. So you do your atomic min with your min value. If the value, wait a minute. Oh shoot. You've got to do X, Y, Z. So if you have multiple threads here in this, it's probably not, you know, you can get contention with one other thread and it's, well, it's the one in your wave. It's the one in your wave. So 0, 1, 2, 3 is your waves, right? This one, you'll be 0 and 2 are together. This one, 2 and 3 are together. So you'll be letting one. Yep. So maybe you just read lane. If you just do a read lane, do a min, and then set it, there's no atomics. So it will be index plus 1. So you get like a read lane index. This is just a 32. If we do any more than a 32, that's really bad, I think. Because 2 to the power of 32 is like 4 billion. We don't want 4 billion nodes. So read thread index. So your read thread index is going to be based on what did I do there? So 0 reads 1 and 1. So 0 just needs to read 1 and 1 will just terminate. And then 2 just needs to read 3 and 3 terminates and it stores it in. So it'll be SV plus 1. And then you terminate if you're odd, right? 0, 1. Yeah, no, but then that's 2, 3. 0, 1, 2, 3. Yeah, C doesn't have lambdas, no, thankfully. Thankfully, no lambdas. Like, because just the type stuff would just be silly. But they've brought auto in, so we could probably have lambdas show up in the next 10 years. Right, so it's got to find a way to terminate these. So the 0 reads 1. And 1 terminates. 2 reads 3. And 3 terminates. Then we need 0 to read 2. And 2 terminates. So you need to have like, we basically need to keep both of them 2 and 3. Yeah, so your one. Yes, you have your own thread index, and you'll have your read index, and your read index always multiplies by 2. Multiplies by 2. And you terminate if you're the bigger than your buddy. Like, how do you know your buddy though? So your buddy is like, so if you're thread 1, your buddy is 0. So you kind of just need to do like an and 1 plus not equal to odd or something like that. Right, and 1. So you want to say like is odd. Wait, is it just XOR 1? Your buddy is XOR 1. Yeah. So your buddy right, so your read thread index is XOR 1, right? Because you're just saying it's the other guy. Yeah, that makes sense. So you multiply, and then you say you want to terminate this thread if thread index is, if my thread, so if the read thread index is less than me, terminate me. So just make it inactive. So there's no need for atomics. So there might be no need for a clear either. Which would be pretty cool. So I think all we need to do is say terminate, then you literally just do, you read your buddy and you've got yourself here. So your buddies is read index. They're in the same wave, so there's no need to bother synchronizing it. You could probably do this in LDS memory and make it even quicker. And you're basically going to say, okay, so you're storing it in, where are we storing it in? We're storing it in node index. And that is equal to the min of f32 times 3. So there's basically no atomics, right? You just coordinate in there and each thread gets terminated one by one. And min. And then it's max, max, max. Okay, so how are we looping this? So we're saying while one, yeah, no, it is a do while. Right, should we read all that, drop some comments down and see what we got? So we're calculating some bounds. So we get the base leaf node index, like so. Yeah, what one, another crash? No. Yeah, these crashes, man. So your node index is leaf node index plus base leaf node. Good. Then if we go outside of the bounds, don't bother doing anything. Makes sense. Base spheres index is base leaf node index times 2 because there's 2 spheres per leaf node. Get the 2 spheres and work out their min and max, like so. Nice. Store that in the leaf node. Yeah, store that in the leaf node. Your thread index is your leaf node index. Your read thread index is your thread index, leaf node index XORed. So if it's odd, it becomes even, and it's even, it becomes odd. So, you know, 0 and 1 are buddies, 2 and 3 are buddies. And you're essentially just like getting your other, you read each other. And you go into this loop, and you say, okay, get the parent for me, given my node index. So you give my node index get, yep. Then your read index, the next one that you read, is, wait, we're doing this too early. You're doing that too early. That comes here on the next iteration. If my read index is less than thread index, then return. So this one means my buddy is going to, I'll terminate while my buddy is going to read this is a write node. the left node thread will take the right, we'll sort of we'll do the min, or do the min max for the parent node. Yeah, we should have really commented this out, or commented this stuff, but anyways, so set the min max bounds for the parent. And then that will say this will advance to the next. So then you'll go into the next one, and that's one you'll read from. And so if your parent is 0, you end. Says a do while. Excellent. So should we put some extra comments in? Base leaf node index, right? So we want to say read the 2 spheres for the, so put that in a block. So read the 2 spheres for the leaf node. Store the, read the min-max bounds. Store the min-max bounds into the sphere, or into the leaf node. Yeah, I'm not keeping my min-max, am I? I've just realized something else that's wrong. Shouldn't it be +1 and +2? No? This is your base sphere. So I've done ×2, right? So this will be 0, 1, 2, 3, depending on the thread index. So ×2, so we could do +0, then +1. I just do +1, +0, so it keeps it the same. Yeah, it's definitely right. So the first thread is going to get 0, 1, second thread will get 2, 3, and so on. No, this is different. So we've got an array of spheres that have been sorted, right? So we need to access the 0 sphere. It's not the tree, it's the 0 sphere. And the, yeah, that makes sense. So we need to keep the min-max and then store it. Just realized. No, no worries, no worries. So we need to keep the min-max so for this parent when we go up, right? So we got the new min-max, and we keep that around. We go up to the parent. Right, I think that seems pretty ideal. Right, so after you've calculated the bounds, you've basically got yourself a tree now. That's fully sorted out, and we don't need to do a clear shader anymore. It's pretty sweet, isn't it? So no need for the clear. We just have to make sure that we're only launching across one thread group for this always. We're not doing 64. We're not doing any more than 4 billion nodes, right? And this will work just fine. It's all in a wave. Wait, you didn't read... Right. So I don't know what's better, reading from main memory. It's probably not, is it? That's reading from main memory. It will be cached though, in probably L1. But you'll be better off just reading your lane, your buddy's lane. So where's that wave read lane? libhcc, third party HCC, libhcc, wave intrinsics. Let's roll. So read lane, read thread. That's our boy. So it's wave read thread. Yeah, we're doing 3 read threads. No, you're doing 6 read threads. I don't know which is better, but we should definitely see how good it is. So we're doing if statement. Compile that if. Right, so that reads from main memory. So you're doing this one reads from the same register, basically. You've got one register. Yeah, we don't know how. So you basically pass in your value register, or not really register, but whatever. It's really weird how this stuff works. It's not with pointers, because min is technically going to be in like a VGPR, like a vector register. Well, sorry, no, it's going to be in 3 vector registers for X, Y, and Z. And it's a vector register because it's a value that's different across each thread. It's all in a SIMD. So you're reading it for that specific read index. So you're getting back your buddy one, basically. So that one you put out to main memory. Yeah. Oh, that one's wrong. Yeah, that's wrong. That should be a node index. Yeah, okay, let's not do this one, because I can't be asked to calculate the node index. We'll just do it with a read lane. We'll see how fast it is. If it's fine, we'll just keep it. So it's a thread index. So yeah, that's what I was doing. Yeah, okay, read thread. Good. Min it with your current one, then store it in the parent. Okay, I think that seems pretty good. Right, so what is left from this? We've obviously got to link this up CPU side. Right, let's get it compiling first. We've got to link this up CPU side. And then we have to change our BVH viewer. Right, because our BVH viewer is now not reflecting this sort of new tree design that we've done. Wait a minute, something's definitely wrong with this. I think we will need atomics, actually. Shoot. Yeah, because that's only going to do 2 nodes, right, 2 spheres in the world, 4, right, 6, 8. Yeah, I thought about this completely wrong. We've got to use atomics. And it's got to launch multiple threads. I think a lot of this is fine. It's just this code has to go back to the way it was. But I've got to calculate that better. Yeah, that works. Sweet. Glad that theme, you guessed it. Let's put that back. Right, so technically this tree, right, it's the number of leaf nodes. You can actually have tons of leaf nodes. Right, I was getting confused by the depth. The max depth is 32, but the maximum of leaf nodes is definitely not 32. It could be a lot, but it could be basically 2 to the power of 32 divided by 2 or something is maximum number of leaf nodes. That's the max depth of a binary tree. So the thing that we calculated wrong, so this is fine. This is fine. It's not read thread index anymore. It's your buddy. So it's in a work group. You know, like a thread group. It's in a thread group at least. So you could know your thread index or whatever. So 0 at this point will be up to 2, even 4 down to 2. Right, my base thread. Right, my node index is that. So to get your friend's node index is that, but then you have to go up the same number of parents that they've gone up. So if you've gone up a parent, no, you just need to read the buddy, like, right? I think it's just this, right? It's just whatever your node index is. So that'd be a 4, that'd be a 5. It's the XOR thing still. So you're just saying, hey, if I'm odd, yeah, it's just that simple. So if I'm odd, this is the right node. So you don't need that read index anymore. So you read calculate the min-max bounds. Okay, something like that. So it's like you're basically doing node index plus 1. Because you know this lane is going to be an even number. Yeah, I think that's the fix. So, do you need thread index anymore? No. So you just keep going up the parent. You want to do that check before you do the parent? Because you'll land on the same parent or something like that. So you say, so you come in here, you got 4 and 5. 5 disappears, right? You need to have read this from 5. Read from 5. Go up to the shared parent and set. Okay, that makes more sense now. Good night also, Red. Thank you, appreciate it, sir. I'll see you in a future stream. See you Tuesday. Have a good start to your work week, by the way. Yeah, so I think this fixes the problem. Right, so you go over all the leaf spheres, set up their, yep. You check if you're an odd one. We say We'll set the min-max bound for the parent node. Fantastic. So this one is saying like, you know, calculate the sort of min-max bounds from the left, right. Yeah, so I guess this isn't that bad way of doing it. Yeah, my only one concern is doing it this way is if you have a massive, like, for 32 threads or whatever that run next to each other, your 0 after 32 have all joined up together by going up the tree, right? These two go up the tree, these two go up the tree, these two then go up the tree. After a depth of 30, wait, is it depth of 32? Wait, when your 32 threads join, so after 32, not sure how many. It's half, yeah, it's half, then half, then half, then half. There's something like, wait a minute. Yes, it'd be 16, then 8, then 4. Yes, it's like 6. So after six layers, your 0, you're only going to be having one thread per wave. One thread per wave is going to be active, but it might be okay. But then for basically you've got a maximum of 32 depth. So then after another 6, so while it's in the next 6, it could collapse some of the waves actually. So it might not be that bad. It might not be so bad. So some of the waves would just finish. All of the odd waves will finish, basically. And there might be a way where you can reorder this. So you're basically, you know, this is a thread in wave 0, like this is a thread in wave 0. So by a wave I mean, yeah, it's 32 threads in lockstep, right? So this would be a thread in wave 1. This would be a thread in wave 0. This would be a thread in wave 1. Okay, so that would be thread index 0, thread index 0, thread index 1, thread index 1. So every single time, but so it'd be wave 0, thread 0, right? Wave 1, thread 1, wave 0, thread. So basically wave 1 is all going to go within the first check. It's just all going to disappear. Yeah, so after the first sort of leaf node, the first layer, wave 1 will just all go at once, right? So there might be a way where we can optimize that. So that'd be a bit of fun to see the numbers, maybe. So yeah, I think there's something we can definitely do that to make it better. So we'll calculate this thing a bit differently, I think. Wherever we use dispatch index will just be calculated a bit differently. We might use thread group. Yeah, it's something like that. And wherever your base, yeah, wherever this thing is used, that'll be used a bit differently to calculate your sort of leaf node index, basically, right? Base, leaf base node index, leaf node index. So the way you calculate this will be a bit different. So I want to jot that down quick. So effectively, like to do, you know, see if you can organize the threads in a wave, or the threads over waves better, so waves terminate quicker. I think there's a better way to do that. Because otherwise you'll have like 32 threads executing in lockstep, but there'll only be one going for a long while. And that's the way the current solution works. But yeah, so that would be the second thing to do. Oh, sorry, that would be the thing to do after we complete it all. So we need to wire this thing in. Right, so what are the steps left to do? Let's jot these down. So we need to rewrite. We need to sort of rewrite the viewer, the sort of BVH viewer. That's all we want to do in it. So sort of like launch BVH, launch BVH count bounds. For, you know, for one thread for each leaf node. Cool. So you want to launch that. Rewrite the BVH viewer to reflect the new sort of like implicit binary tree structure we've got. What's the next sort of thing? Yeah, so after that we can actually view the tree. The next thing to do is actually rewrite the sphere ray tracer to use the BVH tree. So we can actually see how fast it actually is. Okay. And then I guess we can try and optimize it. Try to optimize. Optimize. I think it's called wave occupancy. Because you're saying like, effectively, you're using all of the waves. And you're not having like a bunch of idle threads in a wave. Right. I think I better do it for today. So in the next stream, we'll definitely have these two done. We'll be able to view it, and we'll probably be writing this guy out and maybe even finish it. So yeah, that's probably cool. I'm glad what we've come up with today. It's been really good. So let's find someone to raid. So a stream at 6:30 p.m. GMT. Let's see if there's anyone to raid. Thank you, Anka. I appreciate it. You have a good night too. And yeah, everyone have a good. So I have a Twitter where I post when I have some updates which are visible. There's a Discord if you want to come hang out and have a chat outside of the stream. Also post updates and links in there. There's also a VOD channel if you guys want to catch up on the on everything. There's a VOD channel. Right, let's find something to rate quick. Right, let's navigate Twitch and its terrible system. I just want to find. There we go. That wasn't complicated. Bootstrapping. Oh, that sounds good. This sounds good. This sounds good. But yeah. Right. Thank you all for coming. It's great to have you all here. Yeah. Hopefully we're gonna have this BVH doing something good. Heading off myself, gonna go to the office tomorrow. Oh no. It's pretty cool you get to work from home though. But yeah, have a good trip in, hopefully. Then Poland Wednesday for Code Dive. Ah. What do you mean by Poland Wednesday? What does that mean? Not sure what that means. But yeah, this was a really great resource. I forgot you could do these things implicitly. Are you going to Poland for a conference? Oh, that makes sense now for Code Dive. Right, fair play. That's a lot of traveling this week, actually. Right, have a good start to weekend. I'll see you all on Tuesday, if not Thursday. Catch you later. Thank you. Bye bye.